All right, so last section we're going to look at this week is 3-5. And what we're going to be doing is kind of the same thing we did yesterday. We're going to be finding roots again, except now you might get roots that are complex numbers. Okay? So I've been saying this all week. Okay? We've said it many, many different ways. That if you have a number that is a 0 or a root to your function, that means you can take the number, you can plug it in, and you get 0 for y. That's what it means for something to be a root. It also means that that graph crosses the x-axis at that spot. So if you had a number that was a 0, that means that that number is also an x-intercept. Any question on that idea? Those two go together. Roots and x-intercepts are really the same thing. Now, if we graph polynomial, or if you graph any kind of function, and it never crosses the x-axis, it doesn't mean that your problem doesn't have any answers. It just means that your problem has no real answers. Okay? So let's take a look at this graph. It's a parabola, x squared plus 1. Okay, so x squared plus 1. It's a graph. Where does that parabola cross the x-axis? Yeah, it doesn't. Okay. Now, it has an exponent of 2. Well, we're going to learn in some point later today, you always have as many answers in the problem as your highest exponent. So if that highest exponent is a 2, there are 2 answers to this problem if you were trying to solve for the roots. All right? So when we set it up, plug in 0 for y, watch what happens when you try to solve for the roots. -1 from each side. Now, how do you get rid of an exponent of 2? What do you have to do? Yes. Square root, and that's the problem. So now you're trying to take the square root of each side. And technically, that's the answer. Well, one of the answers. So let me try typing that in on the calculator. Second, square root of -1. Well, actually, let me type it in like this. So basically what I did is my calculator now knows algebra 1. That's all my calculator understands. Okay? It's past algebra 1. So when I ask it this question, it doesn't really know what to do. It says, well, basically there's an answer, but I don't know the answer because the answer is not a real number. Now, if I teach the calculator algebra 2, right, by changing the mode, by doing that, now the number type, the calculator says it'll handle real numbers or complex numbers. It'll handle both. Right? So it's like now the calculator just passed algebra 2. Ask it the same question, it tells you an answer. So we'll talk more about that answer later. But for now, just understand that there is no real answer to this problem because it never crosses the x-axis. So, we just saw that when I took the square root of -1 on the calculator, it gave me I. I'm going to write that down. So, the square root of -1 equals I. Now, if you ask me why, I would say because. That's a definition. It's kind of like if you ask me, how come parallel lines don't cross? Because they don't. That's the way it's defined. Parallel lines do not cross. It's kind of like, why are stop signs red? I don't know. That's the way they're made. It's the definition of stop signs. They are red in the U.S. with white writing. I think they're like that in every country, pretty much. So this just is the way it is because it is. You can't prove that. Now, as long as we all agree on that, then yes, we can prove other things. Right? Like I squared. So I squared basically means this. That's I squared. So what would you get if you simplified that? What is I squared? Yep, exactly. -1. So I squared is the number -1. That's important because anytime we do a problem, if you leave an I squared in the final answer, you haven't finished. I squared can always be changed to the number -1, and then that can usually be combined with something else. Like if you had a 13 and a -1, now you could make it like a 12, right? Questions on that? Now there's a pattern for I cubed and I to the 4th and so on, but we don't really need to know that because they're not going to come up at all. All you need to remember is I squared. That's going to come up a lot. So let's take I, plug it into the equation we just had. We kind of already did this, but let's just see what happens. We take I, square it, and add 1. What did we just say I squared was? Yeah, -1. And what's -1 plus 1? 0. So what you basically just figured out, when you plugged I in for x, you just found a 0 to that equation. Remember, a 0 is something you plug in for that x, and when you do all the simplification, you get 0. Well, I worked. And there's actually a second answer here. It's -I. I and -I, if you plug them in for x, simplify, you get 0. Right? So we just found the root. So we're gonna practice doing some more of this, whether it involves synthetic division. Okay, if this exponent was higher than a 2, we'd have to involve that and the rational root theorem. We might need quadratic formula. Okay, if we can't solve it by factoring. Right? This one's not too bad because it's just 2 terms. So we can solve this just by bringing the 1 to the other side and taking the square root. So that's not a bad one to solve. Okay, but they get a little bit more complex. All right, so kind of the quick overview of complex numbers. I'm going to show you what a complex number is, and I'm going to show you 4 things. Add, subtract, multiply, divide. Okay, those are pretty much the things that you need to know for this lesson. So first of all, how do you write a complex number? The standard way to write it is A plus BI, where A is the real part, B is the imaginary part. So here's an example. 2 plus 3i. 2 is the real part, 3 is the imaginary part. How about in this one? 2/5 minus I. What number is in front of I, even though it's not written there? Yeah. -1. There's a -1 there. So if I just asked you a simple question like, okay, the one that I'm pointing to, tell me the real part and tell me the imaginary part. You'd say the real part is 2/5. The imaginary part is -1. The I is just there to tell you what's in front of it is the imaginary part. Now, if you look at these other ones, these are complex numbers too, like 3i. Think of it like this. There's no imaginary part, so 0 plus 3i, or 0 minus 7i. When the real part is 0, we normally don't write it. These two right here are called pure imaginary numbers because they have no real part. Pure imaginary numbers. This one right here, we just call a real number. What's the imaginary part there? Nothing. It's like 4 plus 0i. Same idea. If part of it is 0, we normally don't even bother with it. We just write the part that's not 0. Okay? So that's a real number. Questions on that? All right. So, first thing I need to kind of make people understand, and this is a little weird, is that I in math is not a letter. Okay? I is not a letter. Okay? Here's another example of that. That's not a letter in math. Now, if somebody was talking about the Greek alphabet, they'd say, yeah, that's a letter in the Greek alphabet, pi. It's one of the letters. But in math, it's not a letter. We borrow the symbol from the Greek alphabet, and it means 3.14. Okay? You'd never write this in a math problem, and somebody would think, oh, that's a variable. No, it's not a variable. Yeah, it's a Greek letter, but in math, we would never use that as a variable. Because everybody knows in math, that symbol means the number 3.14. Okay? It's not a variable. Same thing with I. Okay? Yes, I is a letter in the English alphabet, but in math, that symbol means the square root of -1. So when you're dealing with complex arithmetic problems, you never use I as a variable. That would be extremely confusing, because I already means something else. You want to use a variable? Fine. Pick X. Pick Y. You use a different letter. Don't use I, because it already means something else. Now, even though I technically isn't a letter, if you have 2x plus 3x, and you combine that, you get 5x. Well, if you have 2i plus 3i, and you combine it, you get 5i. So even though it's not a letter, if you kind of think of it as a letter when you're combining like terms, the math will come out right. Like 10i minus 2i is 8i. Just like 10x minus 2x is 8x. All right. So what you're doing right here, and this is, again, it's going to be a little weird, but it's kind of like doing this. Let's say you had 5/8 and you subtracted 2 copies of the 8s. That would leave you with 3 copies of 8. Right? If you had 5/8, not the fraction 5/8, that sounds confusing. But if you had 5 copies of 8 and you subtract 2 copies of 8, you'd be left with 3 copies of 8. So if you do this out, you would get 24. This is what you're really doing right here. 2 copies of I plus 3 copies of the number I gives you 5 copies of the number I. That's basically what you're kind of doing. Okay, when we multiply complex numbers, foiling is going to come up. Okay, some people don't learn it as foiling. They just learn it as double distributive property. So if you learn it that way, that's fine. Bottom line is you're going to get I squareds every time you do it. You have to change I squared to -1. Okay? If you leave an I squared in the final answer, I'm telling you right now, it's wrong. Okay, when we end up doing division, I'm going to have to show you guys what a conjugate is. Okay, so I'll show you what that is. And now let's look at what happens when we have square roots. So I have the square root of -x. What number is in front of the x, even though it's not written there? Yeah. Careful, what number? It's -1. So if I wanted, I could do that. I could put a -1 in front of the x. It's the same thing. Now, anytime you have a product under a square root, you are allowed to separate it into 2 square roots, just like that. So instead of saying the square root of -1 times x all under the same root, I'm going to put it as 2. And the reason I did that is because of this right here. What's the square root of -1? I. So basically, what happens when you take the square root of a negative, so we don't have to go through all these steps every time, the negative comes out in front of the square root as an I. Okay? And the reason why I tried to just explain. Okay, so anytime you've got a square root of a negative, the negative comes out in front as an I. So you could write something like this. I square root of 3. Okay? That would be the answer to the square root of negative 3. I square root of 3. Now, let's say you had to do something like this. Square root of negative 4. Well, the negative comes out as an I, okay? And you're basically left with that, I square root of 4. But the square root of 4 simplifies. Okay, square root of 3 doesn't. What's the square root of 4? 2. So we can write that as 2i. So you might be like, well, why do we put the I after it here and before it here? Because if I wrote this, what's confusing about that? If I wanted these to mean the same thing. The bottom one looks confusing to me. Yeah?
You might think it's the square root of 3 times I.
Yeah, you might think that I is under the square root, and it shouldn't be. So to avoid the confusion, just put the I in front when you have a square root, and then there's no problem at all. Okay? But when you don't have a square root, it's okay to put the I after it because there's no square root, so there's no confusion. Okay? So let's try a couple. Actually, I just did the square root of negative 4. That was 2i. How about the square root of negative 7? What would I write that one? Yeah.
I square root of 7.
Yeah, put the I in front. So the negative comes out as an I. Put it in the front. How about the square root of negative 9? Yeah.
3i.
3i. And now the square root of negative 20. You're going to do it just like it was this problem. Square root of 20. But you're going to have an I in front. So, how does the square root of 20 simplify? Yeah?
Square root of 5 times the square root of 4.
Yeah, so this is the square root of 4 times the square root of 5, which is 2 square roots of 5. So now, what do you think the square root of negative 20 is going to be? Yeah?
2i.
Yeah, 2i square root of 5. Okay, so we might see a couple problems with square roots come up, and that's how you handle square roots. Okay, so now let's look at how we add complex numbers. All you have to do, and maybe you want to write this down if it's helpful, to add complex numbers is combine like terms. What does that mean? You are allowed to add real numbers to real numbers. You're allowed to add imaginaries to imaginaries. Those are your like terms. So the first complex number has a real part of 7. The second complex number has a real part of 4. And the operation is addition. So when I write my final answer, what's my real part going to be? Yeah, 11. So do that first. And now do the imaginaries. The first number has negative 3i. The second number has 5i. Add those together. What will I get for an imaginary part? Oh, Brandon?
You get plus 2i.
Yeah, plus 2i. And that's it. Addition, nice and simple. That's all you got to do. Subtraction, pretty much the same idea as addition. But remember this. That negative, it's almost like it's distributed. It applies to both of them. So you're not just subtracting the 6, you're also subtracting the I as well. So anyone think they can tell me what you're going to get for a real part here? Yep, so 4 minus 6 is negative 2. And the imaginary part? Yep, negative 2i minus another I. There you go. So that's how you would subtract them. Questions on that? Okay, we're going kind of quick because again, this part is all really review. I think example 4 is finally the example that starts the real material. Okay, now we want to multiply. What did I say you have to do here when you multiply? I gave you actually 2 different words because I said some people might have not learned it using this term. Yep, foil. We got a FOIL. So let's start it out. Jacob, what's 2 times 5?
10.
10. And Nakara, 2 times negative I?
Negative 2i.
Negative 2i. Okay, Chris, 5 times 3i? 15i. Now, let's do the last part in steps. 3i, it's a positive 3i times a negative. What's a positive times a negative? So we got a negative. And Sam, what's 3i times I?
Would it be negative 3?
Well, what's 3x times x?
Squared.
So what's 3i times I?
3i squared.
3i squared. Now, we still got some stuff we got to do. All right. We've got a negative 2 and a 15. We can combine those together. 13i minus, we've got a 3. And earlier we talked about I squared. Caleb, I squared can always be changed to what number? Not 1. Okay.
Negative 1.
-1. Now, combine everything else you have, and that's your final answer. So 10 plus 13i, that's going to become plus 3, because that's negative 3 times negative 1. And 10 plus 3 would give me 13. Just a coincidence that it's 13 and 13. That usually doesn't happen. And that's how we multiply. Any questions on that? Okay, so last thing before we start our process of finding roots is division. So to do division, we have to know what a conjugate is. So conjugate, all that means to do is basically change the sign or negate. It's a short way of saying that. Change the sign of the imaginary part. So if you said a number was a plus bi, the conjugate is a minus bi. That's all that the conjugate is. So before we do a full division problem, I just want to make sure we understand what I just wrote. So I'm going to give you some numbers, and I want you to just tell me the conjugate. Okay, so if I had 3 plus 2i, what would be the conjugate of 3 plus 2i? Chris?
3 minus 2i?
Yep, 3 minus 2i. So just practicing finding conjugates. What if you had 4 minus 5i? What would be the conjugate of that? Yeah? 4 plus 5i. How about the conjugate of 3i? Yep.
Negative 3i.
Negative 3i. If you get a little stuck on that one, okay, think of it like this. It's 0 plus 3i. The conjugate is 0 minus 3i. Okay. And how about 6? 6 stays the same. If you're like, well, how come we didn't make it the opposite? Well, we did. It was 6 plus 0i. I made it 6 minus 0i. Plus 0 minus 0, there's no difference. Okay. Questions on the idea of conjugates? All right, so let's do division. So, in order to divide 2 complex numbers, we are going to turn it into a multiplication problem. It's kind of like when you have to divide a fraction by a fraction. You multiply by the reciprocal, Well, we're not using the reciprocal, but we are going to multiply. We're going to multiply by the conjugate. So to divide two complex numbers, multiply the top and the bottom by the conjugate of what's in the bottom. So when you look at example 3, the real problem with that is there's an I in the bottom. You can't leave an answer with an I in the bottom. When I'm done, I want to see an answer that looks like this. Real part could be a plus or a minus, depends on how it works out. I want to see an imaginary part, and I want to see an I right there. That's what I want the final answer to look like. So no I's in the bottom of a fraction like that. So, what I usually do is put parentheses around all that, because we're going to have some distributive, and I don't want to forget it. Now, what am I going to multiply the top and the bottom by? Here?
2 plus 3i.
2 plus 3i. Now, I already know the bottom is 13. I'm going to show you how I figured out the bottom is going to come out to the number 13. That was a trick I did in my head. But let's do the top first. And there's no shortcut for that. You just got to do it out. So 5 times 2 gives me 10. And let's do this at the same time. 5 times 3i.
15i.
15i plus 2 more. So 17i. And now the last part. I times 3i is 3i squared. And what number is that? When you simplify that whole thing. -3.
Oh.
Now, watch what happens in the bottom. And this happens every time you multiply conjugates. 2 times 2 gives me what? 4. 2 times 3i?
6i.
2 times -3i?
-6i.
They cancel. Positive 6i, negative 6i. So when you're doing conjugates, you really don't have to worry about the outer and the inner in FOIL. The only ones that matter are the first and the last. So 2 times 2 gives me 4. Negative times positive is a negative. 3i times 3i. Well, I don't even know why I put that plus there. I can just leave it like that. Because negative times positive is a negative. You're not wrong if you put the plus there, but you don't need it. What's 3i times 3i? 9i squared, which is what number?
-9.
-9. So this negative in the parentheses came from the I squared. This negative outside came from a negative times a positive being a negative. Now, what's 4? That's going to become 4 plus 9, which is what? 13. That's how I got 13. Okay. So the way I did it is I basically foiled it in my head, but I didn't have to think about the outer and the inner. All I did was say, okay, 2 times 2 is 4, and I remembered that. And I said, all right, -3i times positive 3i. What's that? That's 9. So I said, okay, 4 plus 9 gives me 13. So when you FOIL conjugates, it's really, really quick. All right, so now we've got 10. Actually, we can combine. What's 10 minus 3? So 7 plus 17i, all divided by 13. Does this look like what I want my answer to be?
No.
Not quite. Okay, but it's just about there. Only thing you've got to do is separate it into 2 parts. So the real part that would go in the first box is 7/13. And the imaginary part is 17/13. And that's what I'm looking for. Okay. Any questions on that? Okay. So now let's try finding some roots. I want you to keep in mind that everything I've taught you this week still works. You can do the rational root theorem with this. You can use quadratic formula with this. You can use synthetic division. Everything that we learned still works. We just now might get imaginary answers. Now, what's nice about this equation that it's going to make it not too bad? I don't think we can factor it, but what's nice about that one compared to, I'm going to give you one like that later. Why is example 6 worse than example 4? I mean, example 6 has less numbers. It only had 2 numbers in it.
Higher exponent.
It's got a higher exponent, right? So if you have a higher exponent, now you're going to have to use synthetic division to knock that higher exponent down. You don't have to knock it down here. It's already a 2. And Jared suggested factoring, but I can't find 2 numbers that multiply to give me 1 and add to give me 1. It's not going to happen. So I can't factor it. What else can I do? Yeah? Yeah, we're going to do quadratic formula.
If you were to do a synthetic division though, with that, you can still get the answer though, right?
Yes. You would have to divide by a root synthetically, and the problem is the root is going to be imaginary. So yes, you can do synthetic division with imaginaries. We're going to do one. But it would be a very long way to do this problem. But yes, and we'll do one that would be what you just said. But not for this one. All right, what's A here?
1.
B?
1.
C?
1.
Okay, B and C are all 1. So let's solve it. Negative B plus or minus the square root of what comes next? B squared, yep. Then? 4AC all over 2 times A, which is just 2. Now simplify that as much as you can. Negative 1 plus or minus. Well, what's 4 times 1 times 1? It's just 4. What's 1 minus 4?
Negative 3.
Negative 3. So the only thing you have left to do is simplify the square root of negative 3. And that's what I showed you guys before we started the arithmetic. So negative 1 plus, oops, I don't know why I wrote plus or minus twice. Plus or minus, what's the square root of negative 3? Yep.
3i.
That would be the square root of negative 9.
I square root 3.
Yes. I square root 3 over 2. Those are your roots. Now, that's okay to leave it that way, because they weren't picky. They didn't say write your answer in standard form. If they did, this is how it would look. Negative 1/2 plus root 3 over 2i, and negative 1/2 minus root 3 over 2i. This is standard form. Just putting the 2 over each number separate. Okay. And I don't know why, but when they have a fraction, even if it has a square root, they usually put the I after it. Because there's no confusion, at least to me, that the I is part of the square root because it's in the middle and the square root is in the top. Okay. Now, if you did something like this, although technically correct, and I'm not that confused by looking at it, you could accidentally do something like that, and now I'm confused. So just put the I right in the middle. No confusion. Okay. Questions on finding the roots there? And if we were asked to classify these as real or imaginary, what are these, real or imaginary?
Imaginary.
Yep, imaginary. So keep those 3 numbers in mind. 1, 1, 1. Just remember those. Yeah. because the only time we put an I in front is usually when it's just the square root by itself. If it's a fraction, or if it's a whole number or integer, we put the I after. Just that convention. Kind of like when you do slope. You might say, well, why do you put the x right in the middle? 2/3 x plus 6. Couldn't you just put the x in the top and say 2x over 3? Yeah, you could. But usually when we write a fraction with a variable next to it, we just put it right in the middle, just like with y equals mx plus 3. Same idea. So now, look at these two numbers that we just got. Negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. Those two numbers are conjugates. All we did was change the sign of the imaginary part. You didn't even think about it because you just put plus or minus because it's part of quadratic formula. But you change the sign of the imaginary part by doing the quadratic formula. And that's always going to be true. Whenever you solve a problem, you never get an odd amount of imaginary answers. Ever. Okay, think of it like imaginary answers like to stick together. They always come in pairs. Always. And what's nice about it coming in a pair, if you said to me, all right, I'm thinking of a polynomial and 3 plus I is a root, then I would say to you, I know 3 minus I is a root. It has to be. Roots always come together in pairs for imaginary numbers. Okay? If 2 plus 6i is a root, 2 minus 6i is a root. So it's like you get 2 for 1. You find one, you automatically know another one. Now, that assumes that the imaginary part is not 0. If the imaginary part is 0, well, now we're back to the kind of stuff we did yesterday. You don't get 2 for 1. You get one root, you have one root. You don't know another one automatically. You got to do synthetic division and all that. Okay, keep that in mind. Imaginary answers always come in pairs. So, I already told you guys this. Everything we've learned this week still applies. So, first thing we're going to do is show that something is a root. Okay, we are going to show that something is a root. Now, if I wanted to show, let's just make it simpler for a second. If I wanted to show 2 is a root, I would really show that what is a factor? So if I wanted to show that 2 is a root, this is what we did yesterday. We showed that what is a factor?
X minus 2.
X minus 2, yes. I want to show 1 minus 2i is a root. So what I'm really going to show is that x minus that is a factor. Okay, you're always showing that x minus the thing is a factor. So we're really going to divide this into this using synthetic division. And hopefully I get a remainder of 0, which is going to mean that this is a factor, which then means this is a root. Okay? So it's the same approach, a little bit more annoying because synthetic division with imaginaries is a little bit longer, but I didn't give you one with a very high exponent, so it's not going to take that long. Okay? So, put what you want to prove is a root on the outside. What would be my coefficients for the synthetic division? Yep. 1, 0, 1, 10. And you know what? Leave yourself a little more space between them. Maybe like this. Hey, it doesn't start off bad. Bring down the 1. What's 1 times 1 minus 2i? 1, just 1 minus 2i. Stays the same. Now, add up the column. You're never going to have an imaginary number to add. Just reals. Okay, so what's 0 plus what's below it?
1.
What else?
Minus 2i.
1 minus 2i. Now we need to multiply this times that. So let's let's do that off to the side. 1 minus 2i times 1 minus 2i. So here's where, when I taught you guys the multiplication stuff, that's where this is coming in. Okay, let's do it out. 1 times 1? 1. 1 minus 2i? Minus 2i, and then another minus 2i gives me
Minus 4i.
minus 4i, and negative 2i times negative 2i. That's 4i squared. But what number is 4i squared?
Negative 4.
Negative 4. So now, put that answer right here, but combine like terms. What's 1 minus 4?
Negative 3.
Yep, negative 3 minus 4i. And now, add your column. Well, negative 4i is going to stay there. What's 1 plus negative 3?
Negative 2.
Negative 2. Okay, so now we only have one more time, and then we're done. I'm hoping that I get negative 10, because if I get negative 10 plus 10, there's my remainder 0. So let's see what happens. Okay, now what two things am I multiplying together? Okay, let's see what happens. How about, Brendan, what's 1 times negative 2?
Negative 2.
And Eric, 1 times negative 4i?
4i.
So positive 1 times negative 4i.
Positive 1. I'll take a negative. Let's do it negative 4i.
Negative 2 times negative 2i? Emily?
4i.
4i. That's nice. Plus 4i minus 4i. So that's gone. And what's negative 2i times 4i? 8i squared, which is what number? Yep, negative 8. And what's negative 8 and negative 2? Negative 10. Perfect. Remainder 0. So, the quotient doesn't really have any meaning here. Okay, we look at the quotient. I'd never have you look at this quotient to do anything because these are imaginaries. But I would have you look at this. So you just proved that this divided into this without a remainder, which means whatever came after the minus sign was a factor. Now, 1 minus 2i is a factor. What did I say about imaginary answers? Yep. They always come in pairs. So you automatically know another root. If 1 minus 2i is a root, what else is a root? You don't even have to do any work to find it. Yep.
1 plus 2.
Yep, 1 plus 2i. So now you know 1 minus 2i and 1 plus 2i. Yep. We weren't finding all the roots here. All they did was say, show this one is a root. But I'm telling you 1 plus 2i is also a root. Okay, you need to know that. Alright, so I think this is the last one, and then basically telling you what I told you earlier, but I'll put it up after. This last thing I'm going to tell you is that the highest exponent tells you how many answers you're looking for. But let's try this one first. Now, first thing I'm saying is that if you graph an odd degree polynomial, I'm guaranteeing you that it has one real root. Can anybody tell me why? This doesn't happen with evens all the time, but it has to happen with odds. Yeah?
Because it has to turn one less than a degree. Or, so like if it was 3, it would turn 2 times.
Okay, so what does that mean? So why does it have to have a real root?
Because it won't be able to turn away from the x-axis again.
So yeah, the odd degree polynomials have to pass through the x-axis, right? Remember we learned odd degree polynomials, the end behavior? One end goes up, one end goes down, and they're connected. So if you have a graph that goes up forever and down forever, and you never lift your pencil when you draw it, you're going to go right through the x-axis sometime. And that means you're going to have a real root. Okay? You might have more than one real. Maybe you'd have two, maybe you have three. But you're going to have at least one all the time. So, let's look at this one. This is a very good one for the first problem on the test tomorrow. They want you to find all the roots. I'm going to tell you, if you want to know the imaginary ones, and that's all I asked you for, you can't find the imaginary ones directly. The only way to get the imaginary answers is to get the real answers first. So, we already mentioned, I think Emily or somebody told us what I didn't like about that. It's cubed. Right? I don't like that it's cubed. So the only way I'm going to be able to deal with this is to use synthetic division and knock it down to a quadratic. Okay? So, before I can do that, I need a list of possibilities. Does anybody remember the name of that theorem we learned yesterday? That gives us a list of possibilities. Yep. Close. It has something to do with fractions. What's the name of that theorem? Yep. Rational root theorem. So let's make a list of our P and Q's. Okay. What are the factors of P in this one? Plus or minus 1. What are the factors of Q? Not very much interesting happening here. So what are all the possible rational roots? Plus or minus 1. Now, at this step, normally I would take the calculator and I would graph that. And I would see which one of the numbers in this list is close. But honestly, I can plug those numbers in faster in my head than it would take to graph it. The reason why? I don't have that many to try, and I don't have that complicated of a formula. So let's just try plugging in 1. What's 1 cubed? 1. What's 1 minus 1? There we go. We found a rational root. Okay. If you didn't see that, you could graph it. Look at the graph and cross the x-axis near 1. So let's make a list of roots. 1. And we're going to add to it. Yep. Okay.
Zeros is the same thing as roots, right?
What's that?
Finding the zero is like the same thing.
This is exactly what we did yesterday. Yep. Exactly what we did yesterday. So we've got the roots. Now, what am I going to do with this root to knock this cubic down to a quadratic? Yep.
Put it in the synthetic.
Yep, we're going to divide through by the root. And I'm not interested in the remainder. I already know the remainder should come out to what?
X squared.
No. What's 1 again? 1 is a
0.
1 is a root. So if you divide by a number that's a root, you're going to get a remainder of 0. Okay? So what I'm interested in is the quotient. Okay, I want to see what happens with that. What are going to be my my coefficients here? Careful. Yep.
1, 0, 0, negative 1.
Yep. Gotta remember those zeros. Okay, so we're going to get lots of ones and zeros here. Bring down the 1. 1 times 1. 0 plus 1. 1 times 1.
1.
0 plus 1. 1. 1 times 1. You guys are in pre-cal. Negative 1 plus 1.
0.
0. There's my quotient. X squared plus x plus 1. Now I need to solve when that's equal to 0. Does that look familiar at all? A is 1, B is 1, C is 1. We already did that. Right here. A is 1, B is 1, C is 1. So now what you would do in this problem, From this step, you would solve for these roots, but I've already done that back in example 4. Negative 1/2 plus or minus root 3 over 2i. So I'll just put that right here. See example 4. So let's put all the answers in. Negative 1/2 plus or minus root 3 over 2i. So this particular cubic has 1 real, 2 imaginary. Could you ever have 2 real, 1 imaginary? I mean, that totals 3 answers, right? 2 real, 1 imaginary.
No,
Why not?
because the imaginaries like to stick together.
The imaginaries have to come in pairs, so you could not have 2 real, 1 imaginary. Okay? Could you have 3 real, no imaginary? Yeah, that would be something that would look like this if you graphed it. 1, 2, 3. This particular problem, if you graph it, is going to look something like this. It's going to cross 1 time. And that's it. Okay, so I've kind of been saying this as we go, but actually, you know what? Am I going to give you that one? Or yeah, I'll give you that one. Basically, the total number of answers to your problem is equal to the highest exponent. Your highest exponent is a 4. You're looking for 4 answers. Some might be real, some might be imaginary. And remember, roots and factors go together. If 1 is a root, x minus 1 is a factor. If 5 is a root, x minus 5 is a factor. So what the linear factorization theorem says is that if you're trying to factor something of degree n, if you're factoring something with degree n, it's going to have n factors when you're done. You're trying to factor a quadratic, that's an exponent of 2. You're going to need 2 sets of parentheses. You want to try and factor a cubic. How many sets of parentheses would you need to factor a cubic? Yep, 3. Because there's 3 roots to that, which means there's 3 answers. Now, how would you actually do that? You guys should be able to do this at this point, right? You should know how to factor that. You shouldn't be able to do it that quick. I can't do it that quick. But the way I would do it is I would make my P and Q list, and I would find a root that works, divide through by it with synthetic division, and then from there, I'm going to end up with a problem that's factorable. So this one actually factored very nice. Here's another one. This one would come from a 5th degree polynomial, a little bit more than I'd have you factor by hand. Okay, but I want you to just see something. There are 5 answers there. You might say, not really, but yeah, there are. -1, -1, 2, 2, 2. That's 5 answers. But what happened is you have repeated answers. So if you were writing these answers on a test, you don't have to write the same answer more than one time. Just understand that there are 5 answers here. And the fancy word for that is multiplicity. We say that -1 occurs with a multiplicity of 2. 2 occurs with a multiplicity of 3. It just means you get the same answer, this answer, 3 times. So that's 3.5. Any questions on that? So, I'll list off some things that you probably want to know how to do for the test tomorrow. Okay, so on the test, you want to know how to find roots. Finding roots could involve factoring, could involve quadratic formula. Could involve using the rational root theorem. Could involve using synthetic division. All those techniques come up when you have to find roots. Not all the same problem. Know how to do long division. And once you do long division, you should be able to tell me the quotient and the remainder. You should know a quick way to find remainders. I showed you guys a very fast way to find a remainder if that's all you want to know. Okay, remainder theorem. So you should know the remainder theorem. If you don't, you're going to be very annoyed with the problem I give you tomorrow. Rational root theorem, I already wrote that down. But just to give you a little more detail, I'm going to ask you basically to do three things with this. First thing, I'm going to ask you to list possibilities. You're going to make a list of everything that's a possibility. Then I'm going to ask you to narrow down the list. How do you narrow it down? You use your graphing calculator. Because you're going to get a lot of numbers. Most of them won't make sense. Okay, so you're going to narrow down the list. So that's what you should know how to do with that. Roots, quotients, remainders. That's pretty much it. That's pretty much what you need to know for the test. Okay, so homework tonight from 3-5. It's 193. It's 1 through 3, that's just odd. 9 through 13, it's just odd as well. And 25 to 27, that's also odd. So we'll take a look at that tomorrow. I will be after school today if anybody needs any help or needs to make anything up. Otherwise, this will be our second to last test for the term.